Hello everyone, I am Andrea. I work for NVIDIA, and we are going to talk about scheduling recipes, cooking schedulers. I want to go fast with the theoretical aspect because we are all tired. We are approaching end of day, so everyone knows here what a scheduler is. I just want you to focus or highlight an aspect, which is this one. So you can see the scheduler both as a time allocator. You decide when a task needs to run and for how long, but it's also a space allocator, like you need to decide where each task needs to run. And usually when we talk about scheduling, we tend to focus a lot about the timing aspect and not too much at the space, like the CPU allocator. And so let's keep in mind for the whole presentation. So how do we do experiments with schedulers? This is going to be our kitchen, the way that the technology that we can use to cook schedulers. I assume pretty much everyone is familiar with SCHEDX, what it is, what it's not. And anyone is not familiar about SCHEDX? Like, is there anyone that doesn't know what it is? Okay, cool, it's easy. It's just, technology in the kernel that allows you to implement a scheduler as a BPF program. So it's like a kernel module, but it runs in let's say in a safe sandbox. You can't crash the kernel. You're actually running kernel code because there's a JIT, there's a just-in-time translator, and the verifier will make sure that your program doesn't have bugs, such as memory bugs or infinite cycles, stuff like that. And SCHEDX also has an in-kernel implementation. There's a core in kernel that will ensure that your scheduler won't crash the machine. Like if you have a logical error, for example, a starvation or a deadlock, you can specify a certain timeout. And if a task is not dispatched within this timeout, the SCHEDX core would automatically kick out your scheduler. So worst case scenario, your system is frozen for, 5 seconds, 2 seconds, depending on the timeout that you set. And then everything is resumed, like everything transparently moves back to the default scheduler. Another cool thing about SCHEDX is, yes, your scheduler is a BPF program, but there's also a user space program that loads the BPF program. So what you can do, and they both share the address space. So what you can do is you can do something in user space and communicate to the BPF part. You can have like a very efficient communication between user space and BPF, which is essentially kernel space. You don't need like in-kernel APIs. You can just create your own APIs. Between BPF and user space. And typically in BPF, what you do, you just implement some callbacks. There's a callback, for example, when a task wants to run. There's a callback when a CPU is available, and you can do something with that CPU. So at the end, the SCHEDX scheduler is just implementation of callbacks, similar to a module, essentially. And I put here like libbpf rs and libbpf, because, libbpf, of course, is the binding to BPF. Libbpf rs is what we are currently using to provide bindings for Rust so that you can easily implement your scheduler in Rust, and part in Rust and part in BPF code, which is essentially C. So I'm saying this because what's the benefit of moving something to user space? It's the fact that you can reduce the complexity of your code. If you have a chunk of code in your scheduler that is really complex, you can move that to user space and kind of avoiding the limitations that BPF imposes. Because in order to provide you more safety, there are some restrictions in the programming model, like you can't do allocations, and you have the same limitations that the kernel has. So no floating pointers, your stack size is limited, stuff like that. So, you have, like, for example, a load balancer in a scheduler. You can implement that in user space, for example, and you can use floating point. You can even use user space libraries. You don't have language restrictions, because at this point you can just use, I don't know, Rust, Python, Java even, because at this point you're just a user space program. So this looks cool, but is it actually working? I'll show you like a couple of examples. This is gaming. Gaming has been quite successful for SCHEDEX. There's a community of gamers that are actively experimenting with the SCHEDEX schedulers that we produce. This is an example. So what they care is this. I'm not sure if you can see from there, but basically this green light is a little bumpy here, and it's more flat here. FPS consistency means, so this is the frame per seconds over time. And gamers, especially competitive gamers or people that, that they do the speed run, they care about the consistency, because everything it's about how your brain reacts to the game engine in predictable times. So it's not just competitive gameplay like multiplayer, it's also competitive single player. And this is essential to, for those people to, react in predictable very short time slots. I found recently, I didn't even know there are gamers coaches. So one of these guys, there's a gaming coach that recently joined our office hours. So it's quite interesting to see like this kind of job, yes. And so yeah, there's an example. Here's another particularly successful example that we did internally in NVIDIA. This is the Llama benchmark. It's a large language model benchmark. So AI training stuff. And this is not using GPUs, it's using CPUs, because we wanted to show, how can we make CPUs competitive with the GPUs? We can't, but, but we can do better. And this was like a system saturation. We were able to get like a massive more than double, 2.6 times more throughput. And the metric here is tokens per second, if you're familiar with AI. All right, the bigger, the better. Yeah, of course, don't expect, this is like always my biggest disclaimer, don't expect to grab a random SCHEDEX scheduler, deploy in your system with your workload and magically get these numbers. It's not going to happen. Usually you get way lower than that. Actually, in general, you get less than the default scheduler. Because this is all about specialization. So this is like SCX Cosmos is a scheduler that was designed for this specific scenario. If you use this scheduler in another context, it's bad, just bad, doesn't work that good. But the cool thing is that you can, load, unload these schedulers at runtime. They're not crashing your kernel. If they have a bug, worst case, you get like a temporary stall of your system, and that's it. Now, I don't have time to, we don't have time to dig into all the details of these schedulers, but I can give you some hints and some ingredients that you can use in your scheduling recipes if you want to start experimenting. First thing, queues. Schedulers is always about queues. Typically, we have more tasks than CPUs, right? So what do? Someone needs to wait. And how do we determine who goes and who needs to wait? It's using a queue. The easiest way is to use just a single queue, global, shared across all the CPUs. The first CPU available will consume the first task, and that's it. And the math theory tells us that this is the most efficient way to maximize workload, because it's like when you go to the grocery store, right? There's a single line versus having multiple lines. With the single line, you can go directly to the first checkout that is available. So this is more efficient. It also reduces the average wait time, which is great for latency. So this is the best solution always, right? No, Exactly. Why it's not the best solution? Can you spot at least one potential inefficiency with this one? I'll give you an hint. Try to focus, look at the yellow task, the T2. Now it's running on CPU 2. Yes, exactly. There's more migrations. So that's correct. You want a chocolate, the coffee break. No, that's correct. Locality is a problem in this scenario. So there's another one. Let's see if someone is. Sorry, the control? Concurrency of the single queue. Oh, concurrency. Yes, that's exactly the problem. Concurrency of the single queue. It works if you have, like, in this case, we have two CPUs. Let's say you have 1,000 of CPUs that are all hammering in the same run queue. And so when you consume or when you add or remove tasks from the single queue, you need to protect concurrency, so there's probably a lock. If like there's so much overhead if all the CPUs are hammering on the same run queue. So what you do, you create a separate run queue per CPU. That is great, way better scalability, much better locality, because if a task ends up, like the yellow task now is going on CPU 1, it keeps going in CPU 1 all the time. So, and this is actually how the in-kernel scheduler, the default scheduler is implemented. There's a single run queue per CPU. So, all problems solved, right? Not really. Can you see a problem in this case? It's like, yeah, yes. Yeah, exactly. It's waiting. And I mean, there's a CPU available, CPU 1, but T4 is waiting. So we lost, so here everything was amazing in terms of work conservation, but not amazing in terms of locality. Here, much better in terms of locality, but not that great for work conservation. So which one's better? Depends. There's not a right answer. What you can do with this solution is a workaround, which is the load balancer. If you have like a third party, another component in your scheduler that will periodically check if there's an imbalance between the CPUs, and if there's an imbalance, it just reassigns the task and moves tasks around. And this is how the default scheduler is implemented. Why is that? Because in the most generic case, this is the best solution. Like if you don't know how many CPUs you're using, you want the best scalability possible. So that's a better solution. And if you don't know if your workload is going to be cache sensitive, this is the best solution. However, if you have a small system and you don't care much about cache locality, this is probably a better solution. Actually, interestingly enough, with gaming in small systems, this solution it works better. But it depends. If you have too many CPUs, then it doesn't work anymore. So the other thing is how we allocate time to tasks. This is called fairness. I don't want to go too much into the math details. It's just weighted bandwidth allocation. Each task has a weight, and if your scheduler wants to be fair, it needs to assign a certain amount of time over a period of time that is proportional to its weight. That's it. That's all about fairness. Last but not least, topology. Nowadays, topology is a mess sometimes. We have a lot of complexity. Back in the old days, even an SMP system was something very exotic and fascinating. Nowadays, not only we have SMPs, but we have SMT. So cores that are, they can parallelize execution, but they share certain components. So you don't really want to aggressively use them as proper parallel cores. We have caches. So in NUMA nodes, so we have different timing accesses to different area of memory, and even more, we have We may have big little architectures, so cores that are faster, or cores that are faster than others, but the others that are slower, they use less power. So what do you want? Do we want to prioritize the fast cores or the slow cores? It depends. It's even worse. I've seen an architecture recently that has like big cores, so fast cores, with a smaller amount of cache, and slow cores with a bigger amount of cache. That's a pain. That's a very non-trivial scheduling problem, because depending if your task is more cache sensitive or not, you may want to actually prioritize the slow cores for performance. So in order to handle all these possible scenarios, it's not trivial. So sometimes with specialization, you implement your own little scheduler as a BPF program. You try, you test it, and if it works, maybe you get some good wins, assuming you know exactly what kind of workload you want to run, and assuming you have a very specific topology. Last but not least, then we look at some fun things. So this slide probably requires an entire presentation, but I just mentioned this. A task wakes up another. The wakey, where do you want to run it? You want to keep it on the CPU where it's running, or you want to move over to the waker CPU? There's no right answer, because the right answer is I need to predict the future and know in advance if the wakey is going to use the cached data from the waker CPU or is going to use more its working set in the previous CPU. And so if you do some experiments, prioritizing the waker CPU versus the wakey CPU, it's actually pretty easy to do that in SCADX. And you can see completely different results in certain workloads. Other workloads, it doesn't matter, but yeah, that's something to keep in mind. It's another ingredient to keep in mind when you design your scheduler. So let's look at some examples finally. I'll try to do a demo, maybe, if it's working. I don't know. The first one, it's easy. Empty scheduler. It doesn't do anything. Let's see if I can show you the code. I need to increase this. I think you can see now. Maybe. Okay. Sched, C. So all these examples, actually all except one, are in C. This is called SCX empty. So here's the scheduler, just an empty, the boilerplate, and that's it. I didn't implement any actual callback except for the exit. I wanted to show you this because, just so some people don't understand immediately that SCADX has its own scheduler implemented in the kernel. And if you load an empty template, you're basically using the default scheduler in SCADX. It's not the default Linux scheduler, which is the fair scheduler. This is like a round robin with a global run queue. So if you remember from the slides, there's a single run queue shared across all the CPUs. So maybe if you have 1,000 of CPUs, it's not the greatest. But in this case, I can run this one. Okay, and now it's running. Yeah, my system is still functional. It's actually running pretty well. Let's see, I don't know, MGL. Let's try to see if this one is loading. It's actually running pretty well if you don't have too many CPUs. I'm doing, can you see that? I'm doing 60 FPS with this WebGL application. So actually this one is performing sometimes better than the default scheduler, just a simple round robin. But that's because it depends on your workload, right? And let's see. So the other example is a lot more complicated, but I just wanted to show you see the difference between the local and the global run queue, the two different approaches. So if we look at the code, this is just, again, another round robin scheduler. So it's not doing much in terms of time allocation. It's just, partitioning the time proportionally to each task. And you can see, this is a lot more complex. So all the code is on the GitHub page, and I added a link at the end, so if you want to take a look. But so it's implementing a lot of stuff, like this select CPU is a callback that is invoked when a task wakes up. And you can see here, there's a chunk of code that says, prioritize the wakers versus the wakey. That's another thing I want to show you. And then it's doing a bunch of stuff, but it's not that much, it's not that big. It's how much? 148 lines of code. And this is also running, nice. I'm still doing those 60 FPS. Actually, what I should have done, let me see if I can do this. Let's run Chromium here without any, let me move this here, without any FPS limitations. So it goes faster. We see a bigger number probably. Not really, okay, well, that's fine. Well, then we can keep it in the other one. Okay, I was trying to because the refresh rate of the projector is limiting to 60 FPS, which is not stressing. It is not stressing the CPUs too much, but yeah. I see the CPUs are not used a lot, but anyway, it's fine. So this one is using, again, the single run queue. I don't have many CPUs. I have 24 CPUs, which is not small, but everything is functional. The thing is, what happens, being a round robin, what happens if I run stress-ng now? If I run a stress-ng and I use all the CPUs, then everything becomes choppy. See, we're down to 5 FPS. And everything becomes laggy. So instead, what happens if I use, if we use per CPU run queues? I implemented this using the -p flag. So this is the same scheduler with a flag that implements per CPU run queues instead of a single run queue. And let's see if we can maybe move this in the other screen. Okay. And now let's try again stress-ng. Look at the CPUs up above. You see CPU 19 is not used that much, and that's the load balancing problem that I mentioned earlier. Like the game is still struggling because I'm hammering on the CPUs. But now the scheduler that I'm using is not implementing a load balancer, therefore there's no magical load balancing across the CPUs. And without the -p option, so using a global run queue, what happens is, okay, FPS is still struggling, but at least the usage is like 100% on all the CPUs. That's like a visual representation of what I was showing in the slide. There's another thing, like let's say right now I'm always prioritizing the wakey's CPU. What happens if I prioritize the waker's CPU and I'm still using per CPU run queues? And yeah, let's see. I can get lucky or unlucky. Okay, I was unlucky this time. Let's try again. One more time. Okay, yes, now I was lucky. Look at the FPS. Now it's a lot better. Why is it better? I mean, it's not great because it's still choppy, but it's not going to 5 FPS, it's doing 30 FPS. And the reason is not about cache locality, which is the thing I initially thought, like, oh, that's because there's a better locality, and I'm moving the wakey on the waker CPU. But actually, what is happening is, so when a task wakes up, there's a callback in SCHEDEX that you can use, the select CPU. to select an idle CPU. And when I use per CPU run queues, a task gets a CPU and it gets sticky to that CPU. So long story short, what happens here is that one of these CPUs is grabbed by Chromium, and it's not competing with the others. When it happens, I get amazing performance because the other stressed NG are not disturbing the Chromium. And by moving the wake key on the Waker CPU, I'm basically assigning a whole pipeline to a single CPU. So that's the trick. It's not about caching. It's how we allocate CPUs to tasks. It's the space allocator that we mentioned initially. So yeah, I thought it was cool to show you this. Okay, there's a last example, and it's a really dumb one. Is Johannes here? So there he is. So we came up with this idea. I think it was SPM, or SPM for lunch. Yeah, we probably had too many beers, I think, or I hope at least. And we were like, why don't we design like a scheduler that assigns more CPUs depending on the noise level of your environment? So, so yeah, if you use your PC in a quiet environment, and it's just using, I don't know, 1, 2 CPUs, but then you get frustrated, and you like, why don't you go and you yell at your PC and it goes faster? So we can probably show this, maybe. Let's see if it's working. I don't know. Let's bump this up a little bit. So okay, let's go here. I think it's in target. So this is part in Rust because the whole code that is like reading that data from the microphone is implemented in Rust. It's called SCX Loud. Okay, now it's running. Let's stay quiet. Okay, now I need you. Oh, look at that. Clap, everyone. More. I'm just kidding. It's not too much, or you're using too much battery of my laptop. So this is a silly example, but what we have done essentially is to, okay, let's finish the presentation with this scheduler. What we have done essentially is to move a component of the scheduler into user space, because I needed to be in user space in order to do more complex things, such as reading the noise level of the environment from my microphone. And but essentially this is like moving the load balancer in user space, because this is a load balancer. It's load balancing in a dumb way, but it's still a load balancer. And it's really easy. I mean, you can implement the whole thing in user space and pass a number, periodically store a number from user space to BPF, and BPF will implement the logic to distribute the tasks across the CPUs. It's actually, I mean, I wouldn't recommend using this, but it's actually usable, meaning that if you're not yelling at your PC, you're using less power. And I mean, we can probably see that if I do like something like this. Okay, 1, 2, and if I speak here, yeah, we make some noise. We go to 6. So not here, sorry. Here. So you see here we jump from 1, 2 watts to 6, 7. Now keep speaking, so it's consuming power. So it's a way to save power in a really dumb way. But, project these into other contexts. This can be any kind of metric. It doesn't necessarily need to be the microphone level. It can be something in your cloud or some whatever logic you want, and give space to your creativity. Conclusion. Some thoughts, like, the one scheduler solves everything approach, maybe it's not enough nowadays. We have complex architectures, we have different kind of workloads, and we still have, the best scheduler is going to be always the one that we have in the kernel right now. But having a technology that allows you to test different things, sometimes you may get some easy win, and maybe you care about a specific scenario, so that's like, why not? Also, another thing to think about is the CPU, the space allocation versus time allocation. When you want to if you want to experiment with SCADX, this can be something interesting to look about. Again, shared versus local, they're both good depending on your context or your topology or your workload. And the other thing is like wakey. And last but not least, we have the option now to offload something to user space and do complex things in user space and consume them and feed the BPF part with some certain metrics that we collected. We collected from user space. So hybrid schedulers can be a possibility. I added the link to the demo schedulers. This will be in the slides, I guess. If you want to take a look, if you want to reuse the code as an inspiration. Also, you can go to the GitHub page. We also have a Discord server. Community is very welcoming, so if you have questions, feel free to join and ask. And I think that's it. If there are any questions.
Okay. I have a question regarding the user space scheduler. How do you guarantee that it will get some CPU? Because I am seeing a problem here.
Yeah, that's a good question. So I would say it's up to you, meaning that it's up to the designer of the scheduler. Because yes, of course the user space task is a task. So it has a PID and it's scheduled like everyone else. If it's a critical component, or let's say, if it's not a critical component, such as a load balancer, for example, it can be critical, but your system will still be functional. As you're not compromising the functionality of your system. In that case, maybe it's fine to not worry too much. You just boost the priority, and if your scheduler supports priorities that are mapped into weights for SCADX, then you can, give more time slice or more priority to the task. If it's a critical component, for example, we have a scheduler, or rather a framework that is called Rustland, that allows you to implement the whole thing in user space. It only implements like a thin layer in BPF, and everything is offloaded into user space. This scheduler is it's very critical to run the user space component without waiting, because otherwise everything would be stuck. And in that case, we have special logic in BPF so that all the tasks are dispatched before the user space scheduler. And when all of them are done, we always enqueue the user space scheduler. So it works in bars, right? It pushes all the tasks. Then there's no one that pushes all the tasks. So it's its turn, and when it's its turn, it's pushing back, and so on and so on. But there's a special logic in BPF to immediately dispatch the user space scheduler itself, which is a user space program.
Okay.
But, yeah, good question. Okay. No one.
Who was it? So if you use task set to pin, for example, Chromium to one CPU, will it perform the same as what you showed with per CPU work use?
I didn't get, I only got Chromium. Yeah,
No,
sorry.
so if you pin, for example, if you pin Chromium to a CPU using task set.
Yeah, okay. Yes, of course, if you pin Chromium to a CPU, and so the wake-key relationship would be enforced on that CPU. If you don't isolate the CPU, you still have contention with the other stress NGs, for example, when you overload the system. And in that case, like, unless you isolate the CPU and you do something to move away the stress NGs somewhere else.
So yeah, so that's what I'm saying. Like, if you know that this task is important for you, is it better to use KEDX or is it better to just use task set to pin?
It really depends. The scheduling approach, it's more generic. Like you're operating at the scheduler level. Everything else, let's say you can isolate, for example, this subset of CPUs using C groups, for example. That works, but you have to reconfigure or like you need to readjust things. The other thing about the scheduling approach, you can implement soft affinities. Like you're not actually partitioning, but you're doing kind of a partitioning, but it's soft. So when you really overload the system, everyone can also go into the isolated CPUs.
Sorry for that. Just a little comment. We've had a bunch of experimentations around SCADX this year with the team, and we found a tool that's very cool to use for that kind of experimentation, which is Perfetto. It gives you like very natural representations for what the scheduler is doing. So if you want to do some experimentations, use that. It's pretty cool.
Good. Yeah, thanks.
I knew playing rugby as a child would be helpful. You were talking about the wakey problem. Would it be helpful if we tagged the reason for the wake up? And I don't necessarily mean, I'm not entirely sure what I do mean, but for example, we have various ways of waking somebody up. We can do a mutex unlock. We can we can send them a signal. We can have data arrive on a pipe that they're sleeping on, etc., etc., etc.
Yeah, because the thing is, like, the whole thing is about, we have different natures of wake-ups, and if you have a pure signaling wake-up, you don't really want to migrate because you're not producing anything. Instead, if you have a proper producer-consumer scenario, then maybe yes, you want to migrate, unless producer and consumer tend to go in parallel. If they do things in parallel, then yes, you may want to have good cache locality, but at the same time you're spending the precious parallelization advantages. So yes, at the very end, the answer is heuristics, and yeah, tagging can be a way. The other thing is we started to explore ways to keep track of the cache usage and use that as a metric. So let's say if a task is keeping track of how much cache a task is using, if it's bigger than a certain threshold, maybe it's cache sensitive. So either you keep using its working set, or maybe it's not. So you want to migrate easily. So these kind of things.
Yeah, I just wanted to add something to that. So actually it's already in the wake up API. You can signal a sync wake up, but it's just a hint to the scheduler. I believe it's used in a bunch of places, like certainly the binder driver uses it because you have A doing RPC to B and you're certain that A will sleep. The problem happens what happens if A doesn't sleep, because when it's doing the wake up, it's actually awake. So we depend on, when we return back to user space, it better go to sleep, otherwise you've just overloaded the CPU by, pulling. So it's very tricky to, it depends on user space behaving correctly and stuff. But
George, was that wake sync you were talking about?
Wake sync. We use that in SCADX.
Wake sync is a hint. But
yeah,
again, this is sometimes is not working as as you expect. It's not only that, it's also the thing like, yes, a wake sync is like a function call. So you may be tempted to say, yes, always migrate. But first of all, there's topology. Like if the wake is on the other side of the NUMA node,
that's why it's a hint. Like it can be a totally bad idea, and so the scheduler has to decide whether and there's heuristics.
And the other thing is
that it uses.
the other thing is the wake wideness, like how wide is the wake up. We have this heuristic in the default scheduler. Like if a task is waking up all these tasks, maybe you don't want to migrate all of them, even if it's a sync wake up.
Yeah, exactly.
But what I was thinking is to allow experimentation, maybe rather than just having like wake sync versus the non-sync version of wake, whether we could have wake reason that would pass in like this is a mutex unlock, this is data arriving on a pipe, this is a signal, whatever the reason is, and then allow the user space scheduler to experiment with having all of this extra information to guide its decision making. Do you think that would be a useful thing for us to add? I'm not sure. Okay. Yeah.
So I loosely work with the team. I think that we're trying to add features like the user space can give a hint about what I'm trying to do. Like I think primarily it's for about the waker itself, or I gave hint for the scheduler what this thread is doing. But I don't see there's a reason the same interface can be used. Why we cannot use that for like the weaker wiki use case. I'm waking up that guy for different reasons. So there's a user space that should be unmappable, so very fast access to do this type of work.
Just out of curiosity, the communication from the kernel to the user space is BPF ring buffers, just like sending messages. Yeah,
it's basically, so it's a shared address space. So the user space is actually writing into an array or a variable, like a volatile variable, and that's it.
Yeah,
but there are also, you can use BPF maps and have the syscall way if you require special synchronization, or there's the ring buffer as well, in one way and the other. The ring buffer is what Rustland is using to send all the tasks from like kernels, from BPF to user space back and forth.
Yeah, I just wanted to add about the mutex use case. I'm not sure if, because the thing is that it might be a good idea or a bad idea. It really depends on the workload, right? Like if the waker unlocks a mutex that somebody else is blocked on, is it a good idea to pull the contender onto the CPU that maybe it's not a good idea, maybe it is a good idea. So it's a very difficult thing it depends on the user space workload. And so that's why you have to be very specific about, okay, like in the binder case, it makes sense because the user space code that does the RPC will go to sleep. But in the locking case, maybe it's not that obvious. So, but if there's a use case where that, something like mutex, where that information is useful, maybe that can be provided. But I don't think it's mutex, maybe something else. But
yeah, or maybe sometimes the cooperative scheduler might be a good way. So actually the user space, the user application hints a scheduler for certain behavior. Yeah,
I think that writing to a pipe might be more explicit because typically you would prefer to migrate the wiki to benefit from the locality of the pages it is going to read. And in addition, you can expect that it will not take the CPU for a long time because the size of the pipe is limited to what you wrote already. So it could be an example.
Yeah.
Even in that case, I think it may depend on what the pipe is being used for. I'm thinking about make as an example, where you've got all your worker makes, writing their tokens back to the pipe, and you want them to stay where they are because you're making that instance spread your work across all the CPUs on the system. Whereas
yes, if it's a signal in one,
it's only a signal. It's a user space.
Actually, I think pipe is one of the few code in the kernel that uses the wake sync. Because if you do the pipe, it's the wake sync, because it's a kind of function call, right? It's a pure signaling, and because you have a process, when it's done, it releases the CPU and it passes over to the wake key. So it makes sense in this case to treat that as a function call and migrate, but not always, because let's say, yes, in the make scenario, probably yes, but let's say you have a signaling, and then the waker immediately, it's leaving the CPU, and then it immediately needs the CPU again, like in a short loop. Like in that case, wake sync, you shouldn't migrate the wake key. So, yeah.
So you showed us how having everything in user space is nice for prototyping.
I'm not here. Yeah.
So having everything in user space is nice for prototyping and stuff. Have you been able to measure, once I have something that works for my use case, how much more performance I can have by moving from user space and BPF to a proper scheduler written in C in the kernel? Is there a few percent? Is there 10%? Did you measure that?
Yeah, so it really depends. Like, there's not a right answer to that. It depends what you move to user space, because let's say it's a load balancer. At the end, you don't have much communication between BPF and user space. It's probably just a few hints to say, oh, rebalance this CPU or stuff like that. And considering that they basically share the same address space, it's basically a memory write within the same address space. So that's really close to zero overhead. On the other hand, if you're Rustland, for example, that moves the whole logic of the scheduler in user space, that's a big thing to do. Even in that case, using BPF ring buffers doesn't introduce much overhead, because it's all mapped in this. There's no syscall involved. It's just memory copying, and the way that ring buffers are designed ensures that there's no locking. They're all lockless. So, but there is overhead. And the overhead is not about the whole technology. It's because how it's designed is the fact that we need to operate in burst. So, like I was answering your question, like you dispatch a burst of tasks, and then you wait for the scheduler to be dispatched. This bursty behavior, it's actually really good for latency. It's not that great for work conservation, because you inevitably have bubbles in your pipeline. Because you do a burst, and then you need to wait for the scheduler to go, and in the meantime, some CPUs are released, and then another burst goes. So at the end, it's always about the design and the synchronization more than the actual user space overhead. Yeah.
Thank you.